the trig functions. So it'd be better for you to figure out the velocities and then worry about the trig. So let's do it. We have theta 2 prime in there. Oh, here we go. Sine theta 2 prime is in this equation and our third equation over on the other board. So if we solve this one for sine theta 2 prime, then we could substitute the expression involving v1 prime and v2 prime into that other equation over there. So if I label these, when I solve systems of equations, I don't know if you folks do this in your work, because it can get confusing to look at your work later and go, oh, what did I do? So I label them. Equation 1, equation 2, equation 3 when I'm solving systems of equations. So what I'm going to do is I'm going to take equation 2 and I'm going to substitute it into equation 3. And that's going to yield 0.6 equals, and actually I'm going to move the arithmetic over to the other side here. 4 plus 3 radical 3. That's equal to v1 prime plus v2 prime times the sine of theta 2. Now the sine of theta 2, if I look down at that equation, is going to be this expression negative 4 plus 3 radical 3 minus v1 prime divided by theta 2 prime's negative. And now we have an equation that only embodies the two velocity unknowns, two unknown velocities. Matter of fact, look at this right here. I like this. Disappears. Just be careful you don't forget that negative right there. So then v1 prime is just going to be, uh-oh. Oh, thank you. I just told you, don't forget about that negative, and I'm standing here looking at this term and this term going, oh, they're going to disappear.
No, they're not.
No, they don't, because of that negative that I just cautioned you about. Okay? It kicks that all, it changes the signs of those terms, right? Okay. So I'm standing there staring at that. Okay, so anyway, let's see what we get. We get 2.4 right here, and then 1.8 radical 3. And then we're going to bring this becomes positive on this side, that 4, and bring it over, it becomes a negative 4. And then this term right here becomes negative, and bring it over, it becomes positive. And then we end up now having positive v1 prime added to that is 2 of those. So v1 prime is going to be this arithmetic over here divided by 2, because of the 2 v1s prime showing up. So if you punch that out, we should get the v1 prime value. .356.
Yep.
And this should be feet per second, I believe. And then we have an expression somewhere. Well, can I get the other? What did I do? Can I get the v2 prime right now? Should be able to. What I was trying to do was get both velocities before we started working on angles.
If you just plug it into because that one has theta, is what you're saying.
easier just to go for the other angle.
Yeah, I do too. So anyway, my recommendation, which I think I actually even took from the book, where the book suggested find the velocities first, then find the angles, sometimes that doesn't appear to hold. So what we're going to end up having to do here is it looks like we're going to have to mix it up a little bit to figure out some of the angles.
Well, your
Can't solve
angle
a V2.
in both of them, sine of theta 1 prime, you could just solve for theta 1 prime and set them
you have to use
equal
tangent,
and
right?
plug in v
Yeah.
1 prime.
Well, theta, which one?
In 2 and 3, you have sine of theta of 2 prime
Yes.
in both of them. So if you solve for it in both of them and then set them equal to each other, you'll just have the velocities.
Oh, thank you. I knew there was a way to do that. Okay. So we get from equation 3, 2 and 3 again, right? Is what you were saying. As a matter of fact, watch this. If I take equation 2 and write it first, -4 plus 3 radical 3 equals v1 prime minus our v2 prime sine theta 2. And actually we know v1 prime now. This value becomes 3.356. And then if I rewrite equation 3, by kicking the denominator over to the other side, we have that 2.4 plus 1.8 square root of 3 equals that v1 prime again, which is 3.356 plus v2 prime sine theta 2 prime on both of those.
You'd still have to use equation 1.
Yeah, I think I still need to use equation 1. Or,
Let's be set into prime that
No.
V down, that
Yeah.
second V.
I should be able to do it what you said, I believe, right? Unless I'm half asleep here. And so equation 3 becomes 2.4 plus 1.8 square root of 3 minus 3.356 divided by v2 prime. Keep forgetting my primes on there. Watch out for that in your work. Is our sine theta 2 prime.
V2's going to go away.
Now, if I substitute that back into 2, it goes away, so that's not going to help us. What was the suggestion I heard back there?
If you solve for V2 prime in your first equation, and then you substitute it in, you'll get a tangent.
There we go.
Right.
Thank you. So v2 prime, and matter of fact, let me leave this equation with the v2 prime over on the other side then. It's not the most efficient way to do this, but as you just suggested, Joel, now back to equation 1, that we get v2 prime here is equal to 3 over cosine of theta 2 prime. And then we're going to substitute this in for v2 prime right there, and we end up with a tangent expression. Okay? So we get 3 times the tangency. So the tangent of theta 2 prime then is going to be equal to this 2.4 plus 1.8 square root of 3 minus 3.356 divided by this 3 factor. That tangent numerical value is what?
0.720.
0.720. If somebody else would check that out, and then we assign the inverse tan on that and get an approximate reading. Of what? In degree measure?
35.75 degrees.
Got it?
35.75.
So that means this lower mass then is coming off at an angle like this. It came in at 60 degrees. Came in at 60 degrees to the tangency, goes off at about 35 degrees. That's what that's telling us. And then we could then easily substitute that reading and that angular reading back in now to our equation for V2 prime right here. And let me just tuck that result in now over here in the interest of space on the board. Sorry about being cluttered. And this is going to be equal to approximately 3 divided by the cosine then of that 35.75 degrees, which is
3.696.
616.
696.
Thank you. Okay, so there's the final result for that outgoing velocity reading. Okay, words of caution. You saw me make the mistake of forgetting to put primes in several locations as I went, and I caught those as we went along. And then oftentimes what you have to do is step back from systems of equations and look at it. Occasionally you can use matrix methods on these. You can solve systems of equations using your matrix features, your technology. So if you ever start doing more problems with impact type of conditions, which is a fairly common area in engineering. Also, it relates to the more advanced study of elasticity. In one time, I remember in a graduate school course, we were doing analysis of planes hitting a runway, repeatedly. Tires coming down, hitting that pavement. So you got the tires and the mass of the plane contacting the runway, and it eventually degrades the concrete or the material that the runway is made of. And you can actually do analysis to make predictions about durability of materials, situations like that. You also have fatigue testing or impact testing in metallurgy for strengthening surface strengthening materials. So it's a pretty broad area. This is just a brief glimpse of some of the most elementary calculations involved. Okay. Daniel's pondering something, I think. Why don't you catch me after class on that, because I want to make sure I get onto the rigid body stuff, unless it looks like we made a mistake somewhere here. And one thing I did want to check is see if we got the right answers. 3.7, 3.36.
Find the percentage loss.
3.7, 3.36. Okay, we're good on those. Oh, percent loss in kinetic energy. Thank you. Yes. Okay. Well, before impact, after impact. Okay. Yes. So let's take a quick look at that. Are there any questions here? Daniel, you looked puzzled a moment ago.
I guess I'm trying to make it intuitive, which it just isn't.
Could I just
Okay.
one quick question?
Yeah.
And don't have to, if it takes too long, I'll ask it later. The assumption here is that there's no change in momentum in the tangential because there's no impulse, right?
Well, there's no impulse in the tangential direction.
Right.
Each mass has conservation of linear momentum in the tangential direction.
Right, which makes sense.
Yes.
I was just wondering, though, in the earlier questions about angular momentum and linear momentum, where we were seeing objects collide and stick together,
Right.
the assumption is that I'm just making a question, are we assuming that there's no impulse over that instant of collision because it's such a small instant of collision?
They are equal and opposing impulses.
Okay, that makes sense.
That's the key. And that illustration,
Okay, that's why you can make
Yep.
the assumption that there's conservation momentum of the system in the normal direction.
correct.
Okay,
Because,
okay.
and if you look at that little drawing in the book, they showed a force, they showed this lower mass exerting a force, it's sideways though on what their illustration, shows the lower mass exerting a force against this upper mass, and then vice versa. And those are equal and opposing impulses in that normal direction.
So no net impulse in the normal direction.
That's correct.
Okay.
Daniel?
We may have made an assumption so that this isn't true, or might be inherently designed the problem. I'm curious which it is. We have mass 1 coming down and rebounding in the same direction because its closing angle is 90 degrees and its return angle is 90 degrees.
Well, that wasn't an assumption. That was the calculated value.
That's a calculation.
Right.
If a second mass, the one coming up from the bottom, flex at a different angle, it seems that mass 1, that angle should either be less than 90 degrees, or mass 1 should spin somehow.
Well, in the real world, it will spin. But I don't think you want to tackle that at this point.
Okay, so where's the assumption?
Maybe next year.
Where's the assumption where we killed off the angular momentum of a mass?
We're treating these as particles, point particles.
They don't have a radius.
They have no rotational inertia, like a rigid body would, like a sphere
So
or a puck.
So when a lower mass hits our upper mass, we're assuming that the radius of the top one is so small that it doesn't give it any sort of torque to spin.
Exactly. Yep. So the simplifying, matter of fact, very important when you write engineering reports that you write down very clearly what assumptions you're making for your analysis. That essentially covers your ass, because you're basing your analysis upon certain assumptions about the behavior of the material or behavior of the mechanism that you might be analyzing, or the structure, or whatever it might be. It could be a chemical engineering, it could be nuclear, it could be you name it. But make sure you very clearly in your reports write down what simplifying assumptions you make so that you can move through the analysis. And sometimes your boss, manager, and you folks will be managers yourself, most likely after a number of years, is make sure that you're doing the analysis at the level of sophistication that the boss wants. They might say, no, don't treat them as particles. That was a freshman or sophomore level engineering concept. We want you to account for the rotational inertia in those bodies. Then that's going to up the amount of time it's going to take you to do the work. You understand? So just make sure that you very carefully quantify. The research lab I was at before I came here years ago, that's where I really learned about the technical report stuff, was there on writing these technical reports and giving presentations at conferences. And it's almost like being in a court setting where you're getting questions asked of you, or the researchers you're working with are asking you these very substantive questions, and you guys have to work it out as to, well, okay, what level of analysis do we want to really carry out here? And that's where being a good manager also comes into play, because you can kind of direct the staff at the level that you feel is necessary for whatever it is you're working on. And you could send somebody off and they would spend literally years doing an analysis of something, and you just want a quick and dirty something so that you can get on with that project and do an adequate job, or a reasonably professional job of it. Okay. Let's look at the energy loss on this thing. I'll erase some of this. Now remember, kinetic energy is independent of direction. There's no vector stuff going on there, right? And remember how we derive that, I hope. Do you? Go back and take a look if necessary. So anyway, we have each mass. The system is carrying some kinetic energy before. And is there any work done? Assuming these are on tabletop and you're not dealing with gravitational up-down kind of stuff. No, there's no work being done, is there? There's these impulsive forces that act over a very short moment of time, but they're equal and opposing, and there's no displacement there occurring with those forces. So we have conservation of dynamical energy. And there's no gravitational effects because this is a tabletop problem. Tabletop problem. Not worried about the change in gravitational potential. There's no springs. And so what we have is we have the kinetic energy before must equal the kinetic energy in the system after. So in the system before, we have 1/2 mv1 squared plus 1/2 mv2 squared. And that must equal the kinetic energy after 1/2 m. Well, actually, you know what I should do? I shouldn't set it up this way because one side is not going to equal the other. This is going to be a non-zero quantity, isn't it? Because there's an energy loss, and I should not have said 0. Okay. This is the change in energy in the system, and this is going to be less than 0. As soon as I started writing this, I knew something was fishy. Okay, so what we have is T after minus T before is going to be some value. So T after, 1/2 m, 3.356 squared, plus 1/2 m, 3.696 squared, minus the energy before, 1/2 m4 squared plus 1/2 m6 squared. And this is the negative of that sum.
We don't have to take direction into consideration.
Excuse me?
We have to take direction into consideration.
No, as I mentioned a moment ago, the energy equation is independent of direction. Okay. So we're going to pull out a 1/2 m, and then we're going to get these. It's going to be a 3.356 squared plus a 3.696 squared minus 16 minus 36. And you can just look at this and see there's a fairly significant negative value coming out of that.
0.6 times the initial energy.
Excuse me?
Is it just going to be 0.6 times the initial energy because that's a coefficient of restitution and we don't have any strange stuff like mass loss in the system?
Nope.
Okay.
The coefficient of restitution has nothing to do with the acoustic energy loss, the thermal energy loss, or the molecular energy loss due to the elastic pressure wave that moves through the materials. Okay. So does anybody punch a number up right there? Oh, did they give us masses on this thing or not?
Yeah. They just said find a percentage.
Oh, they said a percentage. Okay. Oh, percent loss?
Yeah, so you could just take a.
Oh, thank you. Yeah.
Over
So my calculation here is just going to give you in terms of M, the change, the energy loss in the system, which is the delta E, and that's going to be a negative value function of M. And then the way you do a percent loss or a gain, the way I always remember this is it's always the new value minus the old value divided by the old value. I see people make mistakes with this calculation all the time in business. Percent change or percent loss in an investment, whatever that might be, it's always divided by the old. And then you're going to multiply that times 100. So this would be the kinetic energy in the system after the impact minus the kinetic energy in the system before the impact divided by the kinetic energy in the system before. So you can see that the masses drop out in that case. So what it's going to be is it's going to be this value right here divided by the before kinetic energy term. And the answer on that, I printed out the result, 52% is what that should be. And it should be negative. Negative 52%.
1.67.
They get the energy after is 52, less getting the M out of there. And then the energy before was 24.9 without the M divided by 52. No, I'm sorry. It was the other way around. It's 24.9 is the energy after. Divided out the M.
So it's 50, negative 50.
People are punching away furiously.
Yes.
Did you get the values?
I got half of 52%.
You got half.
Yes. I think I did something wrong apparently.
Keep it 1/2 down.
Yeah, I didn't want to take this much time on this, but we want to make sure we get it right. This book is our textbook is extremely clean, so I doubt if there's a mistake in their answer on this one. So, we have the after. It's going to be involved the 3.356 squared and the 3.696 squared. The before should be the 16 and the 36. Which is your 52. So it should be this. The 1/2 M's disappear.
Yeah, that's.
Is this correct? Okay, and it yields the negative 52%. Thank you. Okay. Good. So let me make mention of a few topics we're not going to cover, but that are included in your textbook. The reason I want to mention them is because you will be taking courses that may involve these topics, and this would be a nice entry-level introduction to that material for you if you are taking some